Hi everyone, and welcome to this video. I'm going to be showing you a visual demonstration of quantum mechanics and explain the math and physics underneath the surface. Quantum mechanics is the study of the smallest particles in our universe, particles at and below the scale of atoms. These include protons, neutrons, and electrons, which make up atoms, and even smaller particles like quarks, leptons, and bosons. These particles don't behave like everyday objects but follow strange and fascinating rules. In this video, I will discuss how an electron behaves inside an infinite potential well. An infinite potential well, simply put, is a container in which no particle inside can escape. If anything inside the container, the well, wanted to escape, it would need to have a potential greater than the container, which, in this case, is impossible. To visualize an infinite potential well, imagine a container with walls infinitely high. To escape, the particle would need energy greater than the container's infinite walls. Hence, any particle inside cannot escape. Before we dive in, here are a few topics that can help you follow along. Firstly, some basic physics concepts like forces, energy, and motion. Second, basic algebra and functions. And finally, how to interpret graphs, particularly XY plots. But don't worry if these are unfamiliar, I'll explain everything as simply as possible. These are the topics I will explore in this video. First is the time-dependent Schrödinger equation, the Newton's second law of quantum physics. Newton's second law is the universal rule that explains how objects move. Schrödinger's equation does the same but for quantum particles. Second is how we visualize the wave function, including its real and imaginary parts. We'll also explore probability density, which tells us where a particle will likely be found. Finally, I'll demonstrate how quantum particles behave inside an infinite potential well with a simulation. By the end, you'll clearly understand these concepts and how they connect to the world of quantum mechanics. Imagine a fish swimming in a pond. The fish isn't sitting still. It moves around, but you can't see exactly where it is at any given moment. Instead, you take a blurry photo of the fish that shows where it might be, but it's not exact. This blurry photo represents something called the wave function, denoted by psi of x and t. The Schrödinger equation describes how this blurry photo changes over time, helping us predict where the particle is likely to be. The left side of the equation, which is I times h bar times d psi over dt, tells us how the wave function changes over time, or how the blurry photo changes over time. I is the imaginary number, and its value is the square root of -1. It is used in quantum mechanics to describe waves. This is h bar, and its Planck's constant, h, divided by 2 pi. It is a tiny number that sets the scale for quantum effects. This is the partial derivative of psi of x and t with respect to time, or d psi over dt. It describes how the wave function changes with time. Just like how the fish moves around the pond, the wave function changes to match where the particle is likely to be. The right side of the equation explains why the blurry photo changes. It combines two factors: the fish's motion, which would be kinetic energy, and the environment it's swimming in, which would be potential energy. H bar squared over 2 meters relates to the particle's mass, m, and the scale of quantum effects h bar. The second partial derivative of psi with respect to x, or d squared psi over dx squared, measures how much the wave function curves. A larger curvature means higher kinetic energy, just like a fish darting quickly creates more ripples. V of x is the potential energy at position x. It represents forces acting on the particle, like currents or barriers. Psi of x and t is the wave function, which shows how the particle interacts with this energy. Schrödinger's equation is essential because it helps predict the behavior of quantum particles. Without it, we wouldn't have the technologies like lasers, quantum computers, or even a proper understanding of atoms. It's essentially Newton's second law of quantum mechanics. Finite difference approximation is a method to estimate derivatives by using the difference between the function's values at nearby points, instead of using the exact formula for the derivative. Imagine trying to estimate the speed of a car. Instead of measuring its speed directly at every instant, you could look at how the position changes over time. For example, by looking at the car's position at 2 nearby times, you can estimate how fast the car is going. Similarly, finite differences help estimate derivatives by using different values. This is the formula used to approximate the second derivative. Let's break it down. What is psi at n plus 1, psi at n, and psi at n1? Psi at n plus 1 is the value of the wave function at the next point. Psi at n is the value of the wave function at the current point. Psi at n1 is the value of the wave function at the previous point. Delta x is the step size or the distance between 2 points in the approximation. The second derivative tells us how fast the rate of change is changing. In this approximation, we use the function values at 3 points, 1 point ahead, n plus 1, 1 point behind, n1, and the current point, n. By looking at the differences between these points, we can estimate how the function is curving. For example, imagine you're driving a car. The first derivative, speed, tells you how fast you're going. The second derivative, acceleration, tells you how quickly your speed is changing. To estimate the acceleration, you look at the point at 3 different times: a little before the time of interest, exactly at the time of interest, and a little after the time of interest. By comparing these positions, you can estimate how fast your speed is changing. This formula is a modified version of the Schrödinger equation, adapted so that a computer can solve it step by step. Instead of working with continuous curves, we break the wave function into discrete points in space and time. This method allows us to simulate how the wave function changes over time in a system like the infinite potential well. Psi n at t plus 1 represents the wave function at position n and the next time step t plus 1. The goal of this formula is to calculate the new value of the wave function based on its current value and how it changes over time. Psi n at t is the wave function at the current time step. Delta t is the small time step size, which determines how far we move forward in time for each calculation. Psi n plus 1 at t is the wave function's next position. Psi n at t is the wave function at the current position. Psi n minus 1 at t is the wave function at the previous position. Delta x squared is the square of the step size in space. Smaller values of delta x give more accurate results, as the approximation becomes closer to the actual derivative. This term, minus 1 over 2 delta x squared times psi sub n plus 1 at t minus psi sub n at t plus psi sub n minus 1 at t, estimates the curvature of the wave function at n, which relates to the particle's kinetic energy. A steeper curve means more kinetic energy. Vn is the potential energy at position n, representing the environment's effect on the particle. Psi n at t is the wave function at the current position and time. This term, Vn times psi n at t, accounts for the potential energy, like the effect of the infinite walls in a potential well. This discretized version of the Schrödinger equation is what makes simulations possible. Computers can't work with smooth curves, so we break the wave function into small steps in space, delta x, and time, delta t. By repeating this calculation over and over, we can simulate how a quantum particle behaves in any system. For example, in this project, we used this formula to model how an electron moves inside an infinite potential well, visualizing both its wave function and probability density over time. The probability density formula is how we connect the abstract wave function to something physically meaningful, the likelihood of finding a particle at a specific position. If you recall from slide 6, the wave function, psi of x and t, contains all the information about a particle's quantum state, including where it might be at any given moment. However, the wave function itself is not directly measurable, it's a mathematical tool. To extract useful information, we calculate the probability density, which tells us the likelihood of finding the particle near position x at time t. This is the modulus of psi of x and t squared, which is the size of the w wave function without considering its direction or imaginary part. This is the complex conjugate of psi of x and t. Multiplying any number by the complex conjugate of itself provides a real and positive number. Multiplying the wave function by its conjugate cancels out the imaginary components, leaving a real value. The probability density formula is the bridge between the mathematics of quantum mechanics and physical reality. It tells us where a particle is most likely to be found if we measure its position. This formula is used to calculate and visualize the probability density of a quantum particle inside the infinite potential well. Over time, as the wave function evolves as described in slide 8, the probability density changes, revealing how the particle's behavior spreads or shifts within the system. The initial wave packet envelope describes the starting shape of the wave function. If you recall from slide 6, the wave function, psi of x and t, represents the quantum state of a particle. At time t equals 0, the wave function begins with a specific shape, which we call the initial wave packet. Psi of x and 0 is the wave function at position x when time t equals 0. This is e to the power, which represents the exponential function. In this case, it shapes the initial wave packet into a smooth, bell-like curve. This is x naught, the center of the wave packet, where the particle is most likely to be initially. This is sigma, and it controls the width of the wave packet. A smaller sigma creates a narrower wave packet, meaning the particle is more localized. The exponential term ensures the wave function starts as a smooth, bell-shaped curve centered around x naught. This is essential because, in quantum mechanics, we often begin with a localized particle that spreads out or evolves. The shape of the initial wave packet determines how the particle behaves in the early stages of its evolution. For example, a narrow wave packet or a smaller sigma means the particle is highly localized but has higher momentum uncertainty, due to the Heisenberg uncertainty principle. A wider wave packet or a larger sigma means the particle is less localized but has a more certain momentum. This formula provides the simulation's starting point, allowing us to see how the wave function evolves. This formula shows how we modify an existing wave packet to include momentum, making it move rather than remain stationary. If you recall from slide 10, the wave packet starts as a localized bell-shaped curve centered around a specific position, x naught. Here, we add a momentum factor to this wave packet. As you know, this is psi of x and 0, which is a smooth bell-shaped curve centered at a particular position. This is e to the power of ikx. This is the momentum factor, which introduces oscillations into the wave packet. K is the wave number, related to the particle's momentum. Without the momentum factor, the wave packet is stationary and doesn't move. By multiplying the initial wave packet with e to the power of ikx, we add momentum to the wave packet. The particle now has a specific momentum and moves to the left or right, depending on the sign of k, which could be positive or negative. The larger the value of k, the higher the particle's momentum, and the faster it moves. The momentum factor enables us to visualize how the wave packet spreads and shifts over time within the infinite potential well. The interaction of the wave packet with the potential well demonstrates how quantum particles behave when they're in motion. Wave function normalization ensures that the total probability of finding a particle in the entire system is equal to 1. If you recall from slide 9, the probability density, which is the magnitude of psi squared, gives us the likelihood of finding the particle at a specific position. However, we don't just care about one position. We care about the entire space where the particle might exist. This is where normalization comes in. The integral sign represents a summation over all possible positions, which is x. This is modulus of psi of x and t squared, as explained in the probability density formula. dx is a small piece of space we're summing over. If you don't really understand this formula, it's alright because you need a fundamental understanding of calculus to properly understand integration. Normalization makes the wave function physically meaningful. It connects the mathematical description of the quantum system to real-world measurements. For example, in this project, normalization ensures that the simulated wave function accurately represents a particle confined within the infinite potential well. As the wave function evolves over time, it spreads or shifts, but its total probability, normalized to 1, remains constant. The boundary conditions of an infinite potential well define the behavior of the wave function at the edges of the well. As explained in slide 6, the wave function, psi of x and t, represents the quantum state of a particle. In an infinite potential well, the walls are infinitely high, making it impossible for the particle to exist outside the well. Psi of 0 and t equals 0, which means the wave function is 0 at the left wall of the well. Psi of L and t equals 0, which means the wave function is also 0 at the right wall of the well. Here, L represents the width of the well. If you recall from slide 6, the Schrödinger equation governs how the wave function evolves. The boundary conditions ensure that the wave function behaves realistically within the confines of the potential well. Because the walls are infinitely high, the particle cannot escape the well, and its wave function must drop to 0 at the edges. By applying these conditions, we can solve the Schrödinger equation for the infinite potential well and determine the allowed wave functions and energy levels for the particle. The energy levels in an infinite potential well are quantized, meaning the particle can only have specific energy values. This behavior is a direct consequence of the boundary conditions we discussed in slide 13, where the wave function is 0 at the edges of the well. This is E sub n, which represents the energy of the particle in the nth energy level, where n is a positive integer called the quantum number. The energy depends on the square of the quantum number n, which determines the number of oscillations in the wave function. A higher value of n means more oscillations and more energy. The energy decreases if the particle's mass m is larger or if the well's width L is bigger, allowing the wave function to spread out more. This formula explains why quantum systems behave differently from classical ones. Particles in a confined space, like electrons in atoms or molecules, can only occupy specific energy levels. This quantization is the reason we observe phenomena like atomic spectra, where atoms emit or absorb light at specific wavelengths. In this project, the quantized energy levels are key to understanding how the wave function evolves inside the infinite potential well. These energy levels define the wave function's shape and how the particle's behavior changes over time. The de Broglie wavelength formula is one of the fundamental ideas connecting quantum mechanics to classical physics. It shows the wave-like nature of particles, such as electrons, and provides a way to calculate their wavelength based on their momentum. Lambda represents the wavelength of the particle, the distance over which the wave associated with the particle repeats itself. This is Planck's constant, the constant we used in h-bar. This is momentum. It is the product of a particle's mass and velocity. Here, it determines how much wave-like behavior the particle exhibits. The larger the momentum of the particle, the shorter its wavelength. This is why we typically don't observe wave-like behavior for everyday objects like cars or people. Their momentum is so large that their wavelengths are too short to detect. On the other hand, tiny particles like electrons have small momentum, resulting in longer wavelengths that can be measured and observed. Now I'm going to show you a graphical simulation that models the behavior of a quantum particle inside an infinite potential well. There are two key visualizations. First, the wave function. You'll see its real and imaginary components, which together describe the quantum state of the particle. And secondly, the probability density, which tells us where the particle is most likely to be found at any moment. Initially, the particle starts with a localized wave packet, and over time, you'll observe how the wave function evolves, spreads, and interacts within the constraints of the potential well. Pay attention to how the probability density changes as well. It's a direct interpretation of the wave function's behavior. Thanks for watching. In the description below, you'll find links to some resources for further learning in quantum mechanics. I've also included a link to a PDF containing 4 different derivations for your reference.